can start. Morning. Today we will talk about design analysis and simulation. Okay. We'll turn off these because that's a bit we'll talk about design analysis and simulation. And this is an important topic in the way that we use BIM. One of the main reasons that we use BIM is for these capabilities. Okay, and today's tutorial in that respect is quite interesting, and you really like it because I think you are in your project for the studio. You are at about that stage, so. At least you can like test some ideas. Maybe it's a bit late, but still it's okay. Better late than never. Yeah, we'll talk about the concepts of representation and simulation, like the relationship, performance simulation, energy, lighting, thermal, analytical models, physical models, and design feedback loops. So we'll talk about these. Basically, the modeling process, in simplest terms, allows us to, represent what the building really looks like, and we take it from there to a stage where we can predict how it will perform in real world if it is built. This is what we are trying to understand. So we'll explore first representation to simulation. How BIM moves beyond drawing, like in CAD or 2D drawings, in terms of simulating actual building behavior, like thermal transfer, daylighting. And then we will see the difference between physical and analytical models. This is a new concept for you. What's that analytical model? What do we mean by that? We'll talk about that. Like the physical model, it was, but abstraction of these is analytical model. We'll go into that. And we have examples of that in the tutorial too. Okay. Then we will talk about the feedback loop, which is important because the design process is an iterative process. Okay. Now you are probably in your design process, you are in your second, third iterations. Okay. And these iterations may be used for refining your building to, like the studio, for your studio tools, refining the building for better performance, okay? So that iteration we'll talk about, okay? So how does analysis, how does, let's say, performance determination help us in that regard, okay? Like, yeah. This is visual, like the 3D shell that we have is the visual geometry, okay? But it also has embedded data like U values, R values, material densities, all kinds of things that we embed in this model. And then we define zones, thermal zones. Unfortunately, I think we're going to go into detail here, but I don't think I talked about thermal zones a lot in the tutorial. Then we will calculate performance, okay, and then we can display the performance in many different ways, like these colors, okay. So let's start with the representation to simulation. As you all know, these are all repeat concepts. Of course, 2D CAD is simply replacing the drafting board, the hand drawings into digital screen, okay. So basically, we create geometry, but we don't understand the behavior. In the first generation CAD applications, we basically use trigonometric algorithms. So basically, they're using a coordination, let's say, system like angles and vectors, etc., to create simple vectors and geometric shapes, where we basically represent the digital diagram of the design intent. Okay, these are static abstractions, as we always mentioned. So they are basically a snapshot in time, and they're just lines. They rely on human cognitive interpretation. So a human looks at this drawing and then decides if that window is too large or too small, or if that building needs a shade. Okay, so we basically do that by looking at drawings and understanding it. Okay, like this is why, for instance, 200 always talks about, draw me a section. Because when you draw a section, you understand how it performs with sun. Okay, so this is why this is important. And this understanding can only happen when your human brain interprets what is drawn on paper. So CAD is efficient, of course, in creation of these technical documentations, but it has no capability to calculate how the buildings will perform. Okay, so the performance part in terms of environmental, let's say, aspect, in terms of structure aspects, this performance cannot be calculated with CAD. So, like hand drawing, of course we use ink, pencils, etc. Like we create drawings, plans, sections, etc. But they don't have any awareness. Geometry without intelligence. It's the same thing on the screen. It's the same drawing. I mean, only drawn on the screen doesn't make any difference. Okay. So at the end, we need to do manual updates. Of course, this is a story of problems with CAD, which I repeated many times this semester. And disconnected data silos, like hand drawings in files, computer drawings in files, which are inaccessible to different people. So that's the problem that we have. Okay. Of course, with BIM, we shift the paradigm. We change the way we work. We shift the paradigm by connecting that parametric digital model, geometric model, with robust physics-based analytic capabilities. So what does this mean? Like this 3D geometry that we create can be associated with rules of physics. Okay, you learn rules of physics in 282, right? So you learn a lot of things about how buildings perform in 232, for instance, right? Structure classes. So these physics rules can be embedded into the modeling environment. That's the idea. So basically, in that regard, that building information acts as a virtual experiment. Because, well, why don't we experiment while we can in the digital realm? Okay, if you postpone it to the construction, then it's going to be costly. So we don't want that, right? So basically, the BIM tools bridge the gap between geometric modeling and analytical modeling. So now, this analytical modeling was already there. So when I was a student, for instance, we were using AutoCAD, but for structure we were using SAP. Okay, and for SAP we were typing the length of columns, length of beams. We were doing that by just typing. Okay, we were typing the code for the building. So with BIM, that connection is now direct. So you create a geometry, you create, and with SAP, as I mentioned, SAP 90, because I was a student in the 90s, so it was called SAP 90, subdoc. Okay. And with subdoc, basically you had to type in the length of structural members, the connections, the nodes. You were actually creating an analytical model by just entering the data, the text. Okay? So that's how it was working. But now we have this, and of course, we were using AutoCAD, and we were using that AutoCAD file, looking at it, and creating a SAP.SUN file, SAP90 file separately. But now with BIM, this geometric modeling AutoCAD file becomes the BIM model, and the structural software is still there. It's robots. It's called Autodesk Robots. Okay, the transfer from the BIM model to the robots model is this bridge gap. It's done now easily, more fluid. Okay, and of course we do simulations. Okay, basically with computers now we can figure out how building can work in real world, and we basically imitate real world physics in that regard. both for structures, lighting, acoustics, energy, solar radiation. There are all kinds of things that we can easily imitate with these physics. Okay, so yeah, this is our model, but you see, this is the analytical mathematical model. The analytical model is very different compared to the physical architectural model. Okay, and it's simpler, but it's focusing on, for instance, here structure. Okay, and then based on that, you decide on what kind of structural requirements that you have, what kind of beams you are going to use, what kind of colors you're going to use. Okay, so that's the idea. So this is what we call building performance simulation, BPS, simulation of the environment. Okay, so basically, project teams can predict and optimize the environmental impact of our building. Okay, in the early stages, early conceptual design stages. You will see, for instance, Autodesk Forma, which you will experience today with the in tutorial. It's amazing. It's very useful. Okay, so basically we can evaluate, for instance, solar installation. How much energy is like being washed down? Our building is washed down by sun. Okay, so that we can optimize site orientation. Like, can I put my building like this way, this way, this way? How can I, orient the building? Which facade is important, for instance? Building massing, like, do I want a slender, like long building? Do I want a compact building? Should it be round? Should it be tall? What kind of mass? And what kind of shading devices do I need? Okay, how do I do that? And you basically, when you simulate these conditions virtually, you basically replace the generalized rule of thumb. What is rule of thumb? We say, for instance, for south facade, put solar protection like horizontal to the ground. Okay, we describe it that way. But with BIM, you can create very complex, let's say, geometric solutions that you can test. You can challenge yourself. Okay, so you basically get a precise data-driven feedback. Okay, so basically you immediately get feedback on your model. Okay, yeah, like you can create heat mapping. Okay, you can optimize the shading devices, etc. So you can do that by making the changes and see how they affect. Okay, dynamic data versus static geometry. Now, our simulation also relies on the non-graphical alphanumeric data in the model. Okay, so what is it? Things like the physical thermal properties in each component, like the reflection, transmission, let's say resistance. We have all kinds of materials, let's say properties, which are the eye in BIM, right? So BIM is not just 3D, we also have many embedded information, the weights. For structure, we are mostly interested in dead weight, right? We are mostly interested for energy efficiency, we are mostly interested in thermal resistance or thermal mass. For lighting, we are mostly interested in the light transmission coefficients. Okay. For acoustics, we are mostly interested in sound transmission coefficients. Okay, so we have many different values. We can basically look into that. Yeah, solar heat gain coefficient of windows. Okay, so basically, when we run an energy simulation, this complex visual geometry is broken down simplified into abstract two-dimensional surfaces because our energy performance software can only work with simplified representation. This is something that we want to deal with. Okay, yeah. So we have parametric objects, we have view factor, like heat loss, solar heat gain, SHG coefficient, yeah, SHGC. Visible light transmission. So these are all basically impacting the energy gain. And then the software basically creates a representation of the results. Okay? Now, basically what we are doing is that we are creating a digital prototype. Because the real thing is expensive. You cannot build and pray God that's going to be good. Okay? So we can basically create a virtual, let's say, prototype, which can be, in that regard, tested. And we basically virtually construct, rehearse, and evaluate. Okay. We also, like we work with teams, we test what if scenarios. What if this happens? What if this happens? So that we can figure out the building is really performing in real life as it should. For instance, you can even test. Normally, I designed this metro station for peak number of 1,000 people per, let's say, hour, okay? But what if we have 10,000 people rushing through? What's going to happen, okay? So you can even test them, okay? So, yeah. So this is the idea. You really want to test what if scenarios. Basically, this is the digital test chamber. Okay, so in this test chamber, you can do whatever you want. It's not going to cost you anything except your time. Okay, but in real life, it's not that. Based on that, like you test, what can I reduce my energy use? Can I test for structural loads? Can I test for cost? So there are all these things that you can test. Okay, and even further, after the whole thing is finished, you can figure out how much of these are really, responding. So in that regard. So let's go into performance simulation, energy, lighting, and thermal. And what do we mean by this? What can we do in that regard? So this is what we call it, building performance simulation. Okay, we basically want to evaluate and predict environmental impact and behavior of the facility in early stages. How does our building work? Okay, so we basically try to figure out how the building will perform in specific specific criteria under specific situations. Okay, so in that regard, we look into orientation of the building, the environmental impact, like in terms of the number of users, the time they spend in the building, the energy requirements for satisfying them, etc. Structural stability or energy consumption, for instance. Okay, we are based on these. We can also look into how we can reduce the carbon footprint of our building. Okay, so we can test if, for instance, changing the structure from concrete to steel, how does it impact the overall carbon footprint? Okay, so we can look into that. So basically, long-term life cycle costs we want to optimize. Okay, so is it the same? No. Yeah, it's the same thing. Okay. Yeah, the siting in that regard. How does it work? Basically with BIM, okay, when we do the environmental assessment, we can figure out how the building on site and how its orientation impacts its, let's say, performance. And we can simulate environmental criteria by using the local weather databases. So this is important. We use weather databases. In different locations, we have different weather conditions, and we have databases that basically represent these. Okay? So compared to these databases, we can test the different options. Okay, like solar gain, shadow casting, reflection, wind speed. We can test all these. You will see how it works in form. Okay, for instance. And then also we can test alternative building massing orientations, like if we change orientation, how does it work? And based on that, we can see passive natural lighting or solar collection. How can we maximize these opportunities in the projects, okay? Or ventilation, shading. So yeah, we are basically using precise data-driven design decisions, okay? So in that regard, we are achieving that. See, here on site, we are casting shadows, we are trying to adjust buildings, like if it's a site with many buildings, we can adjust how they relate to each other. We can create color-coded radiation mapping, okay? We can check the sun path, the shadows the building creates indoors and outdoors. Also, for instance, photovoltaic panels, the form finding. If we think that solar, let's say, solar photovoltaic energy is required, necessary, useful, then we can, test forms based on that. Okay. Thermal simulation. Again, we are trying to figure out the heat transfer from inside to outside or outside to inside based on your time of the year, the climatic conditions, etc., and indoor conditions that you require, okay, and indoor activities that you have. Basically, critical energy flow paths, okay, like transmission through the walls, through the windows, okay, ventilation, solar radiation, internal heat gains from occupants, equipment, for instance, the buildings with many data, like computers, data centers, for instance, they need extensive cooling, okay? Yeah, for instance, you must have heard, right? So all these AI, Google, etc., these data centers, they use a lot of water density, right? So what do they do with water?
Cooling.
Yeah, water is all used for cooling because you spray water and it evaporates. You basically use groundwater, you spray it on the pipes, and you evaporate the water. So that water is lost to the to the sky as vapor. Okay, this is why they're using a lot of water, and you calculate that energy. Okay, so that's the idea. Yeah, we use beam objects to test different assemblies, like based on the layers, how do they, let's say, change the performance of the building, R value. You remember that, right? So when we change the layers in the walls, the R value changes, U value changes, right? And based on that, we can say that we have less energy or less heat loss, it needs less energy. Or daylighting, visual comfort. You can basically simulate the lighting inside, okay? And you can improve the visual comfort, well-being, productivity. You can basically you can basically figure out how the natural daylight, okay, natural light is flowing in the building, okay? You can figure out the track. And based on that, you can figure out what changes that you want to make. But for that, it uses things like surface property data, like reflectance, absorption, or visual transmittance, okay? And we create daylight factor or spatial daylight autonomy. Okay, so these are basically some numbers that gives you an idea of like how your building performs compared to others. Okay? Yeah, so this is what it looks like. And we will be able to do that with Revit. So this is another part of the exercise today. Okay? And yeah, active systems, renewable energy, like how do you calculate the amount of roof or wall space that you can put the photovoltaics and figure out how much energy you can gain from these. So you can create parameterized variables like the roof orientation or roof tilt, and accordingly you can design your project and figure out the results that's working better. Okay? Then we have this concept of analytical model. Let's talk about that a little bit. Okay? The geometric model is basically, as you did with modeling in Revit, the actual physical representation of the physical reality, right? So we have walls, windows, floors, roofs, etc. They are all representing geometrically the reality. But when we are dealing with simulation, okay, we really don't want that much of information. I mean, for energy, all I want is the limits of this space and the openings. Okay, that's all I want. Because if I want to create, because it's abstraction, right? So we want to have a simple abstraction because the rules of physics are very difficult and you cannot have a very perfect, precise result. I mean, there is no need for that. A rough estimate is better, okay? So you don't want to waste time. It takes like, I don't know, 10 minutes to run an energy analysis on a simple geometry, but for that simple geometry, you want to represent it. And this is what we call analytical model, okay? So with BIM, this 3D solid geometry is converted to an analytical model, okay? And that analytical model is sent to the simulation plugins, simulation components, simulation cloud services, okay? So most of these services are running in Autodesk, for instance, when you are using Autodesk products, they're running in Autodesk cloud service, okay? Or you're using a separate software, that software needs an analytical model, a simple model, so that it can run. Otherwise, it's not going to work, okay? So, like you have this physical model, it's the digital twin, right? It's like basically a representation of the physical reality. But if you want to run it in the simulation, finite element analysis, you want it to be as simple as that, okay? This is how you do in Arch 231-232, right? So there you analyze structures using simple parts, right? So the software also breaks that in that way. Stick and node representation, okay? And you basically need to convert them, the model, into these simple representations like that. So this is for energy model. You create building zones, okay? So some spaces are for living, some spaces are just corridors, some spaces are not heated. So you basically define these. And this is the analytical model for the energy. For the structure, as I mentioned, this is the stick and node wireframe. And this is a model, smart baseline, okay? So, and of course, we need spaces where we need to define the specific volumes of air for activities, for human activities, okay? So you create distinct thermal zones, and then you create space boundaries, first level space boundaries, and second level space boundaries, okay? The first level space boundaries are about the bounding space of space width for inside, so, and then the second level is like these surface split, so they basically share only one space one side, like the outside walls, okay? So yeah, you can see the volumes, and these volumes are calculated for their energy requirements and energy performance, okay? And of course, everything is based on data, and this means that our models should include that data. Okay? Basically, the glass, it should have the U factor, it should have the solar heat gain coefficient, and or visible light transmission. Okay, so basically, you need this data in objects, in materials, so that it can be fed into the simulation, okay? So that's important. And of course, there is this model conversion process. This is done in the software. You will also experience that in the tutorial. You basically create an analytical model for energy, for instance. And when you do that, it basically creates a filter, okay, that gets rid of all unnecessary things like the walls, but it uses the walls data about the U. Yeah. then it's replaced with just a plane, for instance. Okay, that's the idea. That conversion is important. We used to use GBXML, Green Building Extensible Markup Language, okay, so that we can translate these buildings into abstract spaces, shapes, but it's not much used today because most of the simulation environments are integrated within Revit, within Forma, within many different software like ArchiCAD. You really don't need to use intermediary, let's say, interface formats. Okay? Yeah, so you basically feed your model, then it takes everything like schedules, weather files, occupancy. Occupancy is important. Some buildings are used 24 hours, 7 days. Some buildings are used only daytime, some offices. Nighttime they are, reduced. They reduce the temperatures, for instance, or ventilation. Some buildings are used only once a month. You can basically put these into the simulations and figure out how it works in that regard. Okay? Geometric simplifications, U values, 3D volumes simplified into thermal zones, technical data like U values, etc. And then as a result, you create an output. In this case, this graph is talking about the GBXML file, but we don't use it much anymore. Probably the software still creates these and sends it over through web, okay, to cloud services, for instance, okay? Or these files are created in the cloud or between cloud services, but we don't deal with these much anymore, okay? So the last part is design feedback loops. Now this is important because we always tell you in this digital architecture studio, the design process is an iterative process. So we make changes, we get feedback from our colleagues, from our professors, from our tests, and then we make changes and do it again. So we continuously change our design. Or code compliance, for instance. There are all kinds of things that you can do. These changes should happen early. If they happen late, it's expensive. Don't forget. So you want to make these changes early. Also, if you make changes late, then we are making cuts, and this is not good. Okay, so we don't want to make cuts to our project. We want to make sure that everything is optimized as early as possible. Okay, so when you move simulation process to the early design stages, okay, then you basically make big gains. Okay, so you have very good improvements in terms of the design changes, which will have less cost impact. Okay, so that's the idea. Remember the McLeamy curve? I talked about this curve before. So this was the ability to make changes. This was the cost of changes. So this is how we used to work. This is BIM. So instead of focusing here, we want to make changes here. So this is where we use, even during schematic design, we can use these analysis tools. Forma is exactly for that. You will see today, in Forma, you create the site, you create your building blocks, you test them for energy. You change orientations, you will have time, maybe later even to make more experiments. In 1 hour tutorial, I only showed a few things, okay? But this will be a start for you. I think I would allow you to try Forma for your studio projects. That would be very interesting, okay? So it's not a bad idea. And iterative feedback. Now, as we always say, design is an iterative process. We have iterations. We make changes, we go back, we make changes, we improve things, we go back. So design is something that constantly evolves, okay? Because old ideas are always reiterated, rethought, reconsidered, reintroduced, new information is discovered, and as a result, our design constantly evolves. This is iteration, okay? So with the simulation software, this prediction of the building behavior is important, okay? Then we can inform the design team with alternatives, and then we can prompt immediate changes to the model, okay? This creates a continuous feedback loop, and as a result, we can do this data-driven process, okay? There is something called plan, do, check, adjust. It is for construction project management. We use it a lot, and it's a Deming cycle. Okay, we basically we design something. We check. We apply that design into our process, into our design, let's say, environment. Then we check it, and then we go back and adjust it. We make changes. Okay, so that's the idea. Okay. Yeah, so you have this model, you basically test it, you run simulation engine, there are issues, you go back, you basically continuously make these changes so that it works, okay? Of course, another thing is that seamless feedback. Now, you will see, I think I didn't make a test of it, I didn't have a chance to do that, but in Forma, you can add team members. It will allow you to add team members, like for your studio project, you can do that as good. You can add team members, okay? And then you can you can basically you can add team members, okay? And then you can create feedback loops, okay? So that's the idea. So basically, in that environment, what we are doing is that we are using the tools to test for different solutions, okay? And we get almost instant visual responses from the environment, okay? And then all these basically get discussed by the team members, and as a result, we can figure out what we can do better for the project. So basically, we are avoiding this manual data re-entry, okay? So when we are working in that same environment together, we basically create let's say a more smooth, let's say, process. But of course, for let's say more advanced analysis, let's say processes, we may have to re-enter changes into the primary model. Okay. Yeah. So here, how we work, if it is disconnected, we need to manually enter the data, which is what we are trying to avoid. So in that respect, Autodesk Forma works really well, okay? And we have this thing called Design Decision Support Tools, okay? Basically, simulation feedback give us this objective data for evaluating computing design algorithms. Now, this is useful in the way that we can provide feedback, okay, to our design team, okay, with these simulation tools, which can feed our discussions with the client. That's another thing. Like, we can basically describe to the client how this new solution, this new, let's say, material, new, let's say, configuration can improve the building, and how much it's going to cost, what will be the long-term, let's say, return easily, okay? So in that regard, as a result, we can prioritize, for instance, the specific energy saving measures, okay? Like how much does it cost to add the shading device, and what do we gain from it, and when do we think that the that alteration will pay back, okay, that kind of stuff. So we have many options. So this is what I want you to test today. Actually, you should be testing 2-3 options, okay, in conceptual massing, which is another part of the assignment today, to figure out, or like options could be also by changing the orientation and figure out how the results change based on that. Okay, so this works great in that regard. And finally, ultimately, we want to feedback the whole process by getting the users, let's say, views. Okay, this is what we call ultimate feedback loop. Post-occupancy feedback. So how do we do that? Well, we can do post-occupancy tests, but we can collect post-occupancy data, but also we can use IoT devices for sensing the temperature in our buildings. We can check the energy usage. We can track the energy usage. We can track the, let's say, comfort, let's say, responses of the users, and then verify how our work has, let's say, responded in real life. And based on that, we can make sure that in the future design processes, we do better buildings. Okay? Yeah. So reality can be captured with physical sensors in that regard, and it can be related to the BIM model, and we can test the real life with the digital twin that we already have. This is what we call a lessons learned database. So we will say that, well, this method didn't work, this method performed great, this needs improvement, etc., and for our future users. Okay. Let's summarize today's lecture. Now, as we know that from traditional two-dimensional drawings, drafting, 2D CAD, moving to BIM, we gain this simulation opportunities, okay? And this allows us to proactively test the design options, okay? And we can improve the building performance in that regard through this data-driven feedback. Basically, we make changes and we figure out what they do in terms of the performance of the building. We can do predictive simulations, okay? So like, instead of static geometries, we can basically see how different scenarios perform environmentally, structurally, economically. So we run what-if scenarios, okay? We need to do analytical abstraction. BIM allows us to do that very nicely. We don't have to do it manually, okay? BIM basically uses that digital model of the building, the information embedded in the model, and converts it into an abstract representation, analytical representation. And of course, iterative feedback. Basically, when you run simulations and when you run it for iterations with your team members, you can improve your project into a level where the performance is increased tremendously. Okay, so that's the idea. Good, I think that's what I wanted to say today. If you have questions, yes?
Is it okay to use LOD100 model to analyze, or rather than LOD300?
Very good question. Now, the conceptual mass model that you will be testing today, for instance, comes as a geometry. It's LOD100. Okay, it doesn't even have walls. Then you clad it with walls. This improves the response of the software. If you don't, okay, if you just want to use the conceptual mass model, you can. In my tutorial exercise today, I added walls like curtain walls, roof, floors, etc. But I didn't have to. I could have just used the conceptual mass model. Then, when you do that, you have to use conceptual, let's say, substitutions. In that regard, the software will say, well, I'm using for this climate, this type of wall. For this climate, this type of roof. It basically substitutes something for you, okay? And uses the numbers from these substitutions, okay? So, or like it will say, the software will say, well, the target glazing area is 45%, for instance, okay? So it will basically adjust the analytical model with that in mind. So if you look at the analytical model that I created today, you will see it's a green-blue thing with some weird geometry. That weird geometry is representing the exterior, let's say, glazing force, okay, because it's calculating a percentage. But you don't have to. You can also create a very complex LOD300 project, and you can run energy simulation based on that too. When you do that, of course, that model will also include like zones, spaces, rooms, corridors, let's say lobbies, etc. Okay, and these will be embedded into the analytical model, so that the analytical model runs smoothly. Okay, so that's the idea. And yeah, so at the end of the day, regardless of your LOD level, okay, the software basically simplifies them into a simple analytical model. So you can have a wonderful steel structure. At the end of the day, it's just sticks and let's say planes. That's the idea. Okay. Any other questions? Good. Now today's tutorial is about two different environments. The first one is Autodesk Forma. It's new. It's a web-based tool. Okay, but you have to sign up to it. Yeet has done it and it works. Forma for buildings, and you basically subscribe to it. You sign a 1 year, let's say, license, let's say agreement, and it works in Autodesk. Okay, and once you start using it, it's going to you have to go to a website, which I also put the link for. Okay, an application website. And you will basically enter certain, let's say, answers for a questionnaire. Don't worry too much about it. And then you'll start a team. You can start a team with your friends, or just, you don't have to start a team at the beginning. You can create a new team later if you want. And then in that software environment, after following my tutorial, you'll be able to see how you can create sites, the buildings, etc. Okay, and do analysis. The second one is, there are two tasks today. The second one is using Revit. I want you to create a conceptual mass, several masses actually, to compare the performance. Okay, and you can use that to basically test for different analysis. And the last one is, actually there's a third one, which is included in the second one. In Autodesk environment, I want you to do a root analysis. Like, how can I know? I did it, I'm showing it at the end of the tutorial. Like, how can I go from one corner to the other corner of a building? It calculates the root and how much time it takes, the length. And this is good for instance, transportation buildings or security of the buildings, etc. Okay? Good. All right then, I'll stop here and we'll see you next week. And before I continue with that,